So we got about 2 weeks.
Yeah.
All right. All right, so the last couple of weeks, those are extras. So we're going to be dealing with Maxwell's equations, and really this is going to be the propagating form. It's the lead-in for the next course. So I like to, there's a lot of ways to teach this. In Whitmore's book, he kind of goes through and brute forces and beats up some of the curl equations to get the solutions, and I don't like doing that. I like to just do it the classical way, so I'm going to do it that way. Now, y'all, have you all had propagating wave theory? You've had the, you know, there's the diffusion equation, the wave equation. Did you have these in physics? I'm not sure how they teach this. Okay, so when you have wave propagation, well, it has to do with the second order in time differential and a second order spatial differential that are going to be coupled. And I'm just only mentioning this because some of you may have had this in physics and may ring bells. But I'm going to go ahead and I'm going to develop the wave equation. And if you want to know where I'm at, this is going to be section 5, 6. But I'm doing it differently than he does it. So when you start with any of these, whenever you're doing any electromagnetic problem in the known universe, you start with Maxwell's equations generally. So I'm going to start with curl of H is equal to J plus the partial of B with respect to T, and curl of E is equal to minus dB dt. Now these are the probably the most basic form of Maxwell's equation. They're in the time domain, and they're spatial derivative operators of curls. The coupling is J is equal to sigma E, and D is equal to epsilon E, and B is equal to mu H. Now, sigma, epsilon, and mu have to do with the material parameters. If you're in free space or in a vacuum, sigma is 0. Y'all follow me on that? Sigma can only have a non-zero value if there are actual charges that can move about. It has to have matter. Now, mu and epsilon have values in a vacuum, mu naught and epsilon naught. And from those two values, we get the speed of light. As a matter of fact, James Clerk Maxwell, long ago, went ahead and he used the known laws and he deduced the velocity of light. Actually, this is very interesting, and it was, you know, you all know that the velocity of light is a constant in any reference frame. Did y'all have this in modern physics at all? All right, it doesn't matter what reference frame you're in. The speed of light is a constant. You can actually get that from Maxwell's equations, and he's a very famous fellow. He did things that other people, you might say, got credit for, but he was the guy that really came to terms with this just on physical laws. So these two equations are absolutely true. Does anybody remember what the name of this guy is right here? Ampere's law. The curl of H equals J, and has to do with Ampere. And this one, Michael Faraday's law of induction. The two things, both based on experimental data, mathematical equations that are always correct in terms of how they define what goes on. So if we take these two things, what I'm going to do is go to the frequency domain and talk a little bit about phasors before I actually start brute forcing these. Now, y'all have had phasors, right? Remember back in the day when you had circuits, you just listen up, you don't have to write this down. When you had circuits, do you remember how if they put plus to minus like 10 cosine of omega naught t plus 30 degrees, here's a voltage, and then they had a resistor R, and say they had an inductor L, and they wanted the time domain current I of t. Now, I don't know if Dave Irwin did it this way or not. Dave Irwin said it. If you had, how many had Irwin? Irwin usually just goes through this and then sticks in the phasor domain, period. Now, a phasor domain means that it's a constant frequency. Y'all follow me? It's got a constant sinusoidally varying term there for voltage or current that's the driving function. If that happens, we could solve the differential equation. Y'all follow me on this? I could say that this voltage, and you don't have to write it down, just listen to me, cosine of omega naught t Really, it shouldn't be 30 degrees here, but I see that in Dave's book. It should be in radians, because omega is always in radians. Y'all follow me? It should be in radians, and that would be pi over 6, but I'm going to leave it as 30 degrees here. That would be equal to, well, if you have I of t here, the voltage here would be I of t times R, right? And then plus the voltage across an inductor is L times di dt. Now you realize that's the differential equation that describes that. If you're a physicist or a mathematician, you might try to solve that problem this way. But we're electrical engineers. We don't do that. What we do is what? We take this voltage and we make it 10 at an angle of 30 degrees. So, y'all remember this? This is a phasor. Now we're getting rid of the actual cosine variation. We know it's varying like this. We know everything's varying at that frequency. We make this 10 at an angle 30 degrees as the voltage source. And then instead of having L there, what do? We put inductive reactance there. Y'all remember that? Now this would become simply J omega naught L as an impedance, correct? I'm going through this for one real big reason, because if you see how much easier it is to solve these things with phasors, then you'll have an appreciation for why phasors, when I solve those things up there, are so much better than writing differential equations and getting the general solution. So now if I wanted I of t, what I'm going to start with is getting I phasor, right? I guess Gross makes you put a little tilde over the top. Doesn't he do that? How many have had Gross? Doesn't Dr. Charlie Gross make you he makes you define things with tilde for a phasor or not? No?
Yes.
Well, it's implied. If you see a J omega, you're in the phasor domain, but I don't argue with him about that. So if I wanted this I phasor, I would say that would be this voltage, which would be 10 at an angle of 30 degrees over R plus J omega L, or omega naught L. Do y'all agree? And we know that's going to be a magnitude at an angle. Y'all agree with me? So I can say this is some magnitude. I'll just call it IM, and it's at an angle theta, and I'll call it theta I. Do y'all agree with this, class? If I give you omega, R, and L, you can give me that. You can give me exact value. Remember, that's a phasor. Remember this when you go for a job interview. If anybody gives you one of these kind of problems, don't do it with differential equations. Go right to the phasor domain the minute you see this cosine or sine of omega naught t in there. Now, when I come over here, if I wanted to go to the time domain and get I of t, do y'all remember how to do that? Anybody? It's something you don't even think about. You know it. Normally you would do what? Technically it's the real part of, and then it would be e to the j omega t times I phasor, right? I phasor would be Im e to the j angle of theta I. Now I'm putting this from a polar into an exponential form. Y'all remember doing this, class? Now, the next thing is when you're doing this, you see that I of t here would be equal to the real part. Im's a scalar. And now I add these exponentials, and I have e to the j quantity omega t plus the angle, theta I, whatever the angle is. Y'all agree with that? Now, actually, I can say that this, anytime I have e to the j anything, I use Euler's identity, and I said that's cosine of omega plus j sine, of theta, plus j sine of theta. Do y'all remember that, class? In this case, my theta is really omega t plus the angle, isn't it, class? The real part of that is just the cosine. When you see a j, that's imaginary. So when I take just the real part of this, I get I of m right here, and then I have cosine of omega naught t plus this phase angle that has to do with the current. And now I've solved for I of t here. There's one thing about this, though. The way I've solved it, I've assumed that this voltage has been on forever. There's no transient nature to it. If there was a transient nature, then I'd have to account for that. But here, it's constant. Y'all with me? So that's phasor analysis. applied to this. The key thing that links this is once you have a phasor quantity like that, to get the actual time domain quantity, you have to take the real part of e to the j omega t times the phasor. How many remember doing that, whether you use it every day? Remember that when you had circuits, doing that kind of stuff? A lot of times in circuits, they don't ask for the time domain form. They just want to know magnitude and phase of either the voltage or current, and that's it. But this is really the way to complete it, because you remember, in the phasor domain, you can't observe that theoretically. You can observe time domain things, not phasor domain stuff. So that's the reason they do it that way. Okay, now, back to these things. So now, I didn't show, well, I did show you. Remember I had L, I replaced L by J omega L, right? Because it was the impedance. So now, the real truth is anytime you have a time derivative, if you're going to do something that's in a phasor domain, a time derivative just brings out a J omega. Do y'all follow me on that? So, now I'm going to go ahead and show you Maxwell's equations in the phasor domain. First, I'm going to go ahead and take these equations and I'm going to replace, I'm going to get them down and just, I want only two terms in here, so I'm going to have H and I'm going to have E. So when I go here, I take this one and I make that sigma E, all right, by replacing J, then I have plus epsilon dE dt here. And for this one, I'm going to say that's really minus mu, just mu, times dH dt. Now what I've done is, I've used this coupling equation, and this coupling equation, and this one to get everything in terms of just H and E. Y'all follow me? All right, it's important to understand. The reason I'm doing this is I'm trying to reduce the complexity. I'm working my way towards something that's manageable. Now, when I have these two equations right here, I'm going to take everything to the frequency domain. So the first equation here becomes curl of H is equal to, now remember, I got a sigma here, but every time there's a time derivative, I bring out a J omega. So it's sigma plus J omega epsilon times E. Y'all follow me? How come that happened, everyone? All right. Then for the next one down here, I have curl of E, pardon me, is equal to minus simply mu times dH dt. Or, I'm sorry, my bad. Minus J omega mu times H. I got rid of that time derivative. Now I have two things that are in the phasor domain. Y'all with me? Now, after that, I'm going to go ahead and I want to get one equation with one unknown. If I don't do that, I won't be able to solve these things. So my goal is to get one equation with one unknown. I ask this. You guys got any clues how to do that? You actually know it, kind of, but you haven't used it in a while. Well, anytime you see curls, take a look. If I take curl of E here, what do I get? I get minus J omega mu times curl of H, don't I? Take a look, right? We're assuming mu is not a function of position, so that's a constant. Y'all follow me? Now, if I have that, what might I do to get an equation just with E? Look at the first equation. You see how you have curl of H up there as just a function of E? That's exactly what happens. I take this equation, then I make a curl of E is equal to minus J omega mu times curl of H. Well, there's curl of H, so that's sigma plus J omega epsilon, and it's times E. Now that one you write down. There I have an equation with just E in it, nothing else. and a bunch of constants, material parameters. You all with me? Now we're going to take this and we're going to modify it so it's manageable. First, there's a vector identity that I don't expect you to know, but a curl of E can be expressed as the gradient of the divergence of E minus del squared of E. And that's equal to minus J omega mu times sigma plus J omega epsilon times E. Now, I've just rewritten the last part. Y'all with me on this, class? Okay. Got one equation with one unknown. I've used a vector identity to bring it down to there. But here's where it gets interesting. Now, this is in chapter 6 of Wentworth's book, but not in chapter 5. Chapter 5, he just has you brute force a bunch of stuff and drives you nuts. So I'm just showing you the way you really do this. This is the classical way. So now, you remember what divergence of E actually equal? How many remember it's rho V over epsilon? Anybody? That's Gauss's law, point form of Gauss's law. Usually you're used to seeing its divergence of D is rho V, but divergence of E is simply rho V over epsilon. Y'all with me on this? Okay. Now what they do at this point, here's where we start. We have to make assumptions. I mean, you're not going to solve that for the general, in general, all right? Because frankly, that's a doctoral level, well, master's doctoral level kind of problem for the general form of that in any coordinate system that we talk about routinely. But so we're going to have to make adjustments. So the first thing we do is we assume that it's a charge-free region. Or really, divergence of E equals 0. With me on that? You could say rho V equals 0 as well. Follow me? All right. We're not hurting ourselves with that one. That's generally true for almost any kind of propagating phenomenon. So that gets rid of this term. All right. After that, we do another thing. And I'm trying to do this in a way that it should make sense, the reasoning behind it. The next thing, you see all these constants here? Well, those constants are kind of irritating. And that's my word now. So what we do is this. We say that gamma is called the propagation constant, and it's equal to some alpha plus j beta, and it's equal to the square root of j omega mu times sigma plus j omega epsilon. And so now what I'm going to do is say, I'm going to introduce that constant gamma instead of writing all that crap out. You all follow me? Now you remember gamma when we did transmission lines back in the day, gamma had alpha plus j beta 2. Alpha had to do with the attenuation, and beta had to do with the wave number. So this is gamma, and that's just the propagation constant. And I come over here, and now I can see I've got rid of that. And if I take this to that side, I get 0 is equal to del squared of E, and it's going to be minus gamma squared of E. And if you take a look, see, I took the del squared operator to the other side, set it equal to 0. You all with me? Things are getting a little more compact, a little more doable. Now, at this point, this particular thing is the wave equation, and you can solve it for pretty much just about anything in cylindrical, anything in Cartesian, and anything in spherical coordinates, and it's a boundary value problem, but it uses, in spatial coordinates, you're going to get either Bessel functions if it's cylindrically solved, or you're going to get Legendre polynomials in spherical Bessel functions if it goes to spherical coordinates, and that's well beyond anything we care about. So what we do is this. We're going to find the solution to this, but we're going to find the solution to this thing for the most important in classic cases. And that means we're going to assume an electric field has only one component and it's propagating in only one direction. Now some of you may not like that, but you're going to have to appreciate this. If you have an electric field, in general, an electric field like this kind of equation, the electric field could have three possible coordinates, or three possible components that are orthogonal. And it could be propagating in any direction, right? That's not of much interest to you guys. You just have to find out a little bit about this. We're going to talk about an electric field that's polarized in only one direction and propagating in only one direction. So remember, an electric field has a vector direction. So when we do that, and I want to make sure I went where it breaks out a lot of the constants and stuff, and I'll get to that. But what he doesn't do in that chapter is the thing I'm talking about is on page 323, and it's the solutions to unweighted propagation. So now, when I do this, here's what I'm going to assume. I'm going to come back over here. While I'm doing this, did anybody go to the A-Day game? Me either. But I saw a bunch of posts on social media about some of the duds that supposedly we have. I don't know if it's true. Just wanted to ask the class. Okay, I'm going to go over there and I'm going to take this equation. Actually, I'll bring it down here one more. And now I'm going to say this is what we're talking about. We're in a charge-free region, and we're talking about wave propagation where we have an electromagnetic field that's polarized, and I better give you some context to this. This is going to be the x-coordinate, or the x-axis. This is the z-axis. So y would be out of the board. This is a little different. Y'all follow me? We're going to have an electric field that's polarized in the x direction. You're just going to have to go with this one. So it's polarized in this direction, in the x direction, but it's propagating in this direction. So it's propagating in the z direction. Y'all with me on this? Just let me finish and hopefully you'll see why. So when I take a look at this del squared operator, I'm going to do it in Cartesian coordinates. In general, when you have del squared of E, you're going to have three different derivative operators for the x, y, and z coordinate. So that's 9 terms. Now I'm just going to break this up. This del squared operators, if we assume only E is equal to some E naught, well really just in the x direction, I'll just call it EX is going to be in the AX direction is the E field. Then when I do this, I have the second derivative of EX with respect to x squared plus the second derivative of EX with respect to y squared plus the second derivative of EX with respect to z squared. And it's in the AX, this is the AX component. Now, if there were, just for the record, this is a vector Laplacian. You see, the E field's a vector, not a scalar. In the back of the book, if you look at the scalar Laplacian, it would just be the second derivative of whatever that function is that's a scalar, which could be v with respect to x squared, second derivative of v with respect to y squared, plus second derivative of v with respect to z squared. And that's the one where you get basically this is equal to minus rho v over epsilon. Do you remember that? That was Poisson's equation. We did that earlier in electrostatics. Well, that's a scalar Laplacian. This is a vector Laplacian. So I say E field only has an x component. Therefore, I take the derivative of EX with respect to x, y, and z in the AX direction. Y'all follow me on that? Now here's the caveat I made back here. I said I have EX, only EX, but it's only propagating in the z direction. Do y'all follow me? That means there's only a variation in the z direction. That's called a plane wave. Now, are you familiar with that term plane wave or not? No? Plane wave means that if you have something like, if you just think of a two-dimensional plane wave, when you have drop a pebble into water, the rings spread out, right? You get far enough away, it looks like what? If you're just on the crest of that wave, it looks like it's just a straight line, isn't it? It looks like a planar propagation, right? So with plane wave propagation, what we're really talking about is something that is launched a long way from the observation. So it looks like there's absolutely no variation, there's no curvature in the front of that wave. So I come over here, and I'm assuming that the thing only varies with z. Now, if it only varies with z, this derivative goes away and this derivative goes away. Y'all with me on that? So now I go to that del squared equation, and really I just have second derivative of ex with respect to z squared, right there, minus gamma squared ex equals 0. And that is a one-dimensional equation. Well, it's an equation that has only variation in one dimension that represents what the plane wave propagation would be in terms of a differential equation. A lot of this is very abstract, so I'm trying to bring this down to something you can appreciate. All right, when you look at this, this is a simple second-order homogeneous differential equation, right? You could do it, you remember Laplace transforms? We could get the solution with Laplace transforms. Do you remember integrating factor back in the day when you had? Sure, you could do it either way. The solution is simple. It's this. Ex is simply some ex0 plus e to the minus gamma z plus some ex0 minus e to the plus gamma z. Now it's in the x direction. That's the general form of the solution. This looks exactly like propagation on a transmission line. You remember, for a transmission line, you have some v0 plus, and then you would have e to the minus gamma z, and if it was lossless, it would just be minus j beta z, right? Plus some negative going wave times e to the plus gamma z. So this e minus thing just means it's the negative. That's the general solution. Now remember, that's a phasor, right? Just hear me now. Y'all with me on this? That's the general solution. We've assumed that we've got plane wave propagation. We're a long way from the source. Think of a radio station. All right, we're a long way from where the thing launches the wave. And now we're taking a look at the actual propagation at a great range, a long way away. It's going to be like this. Now, when you have this, come over here, and what actually happens is this. If I wanted the time domain form, if I wanted E field in the time domain, say as a function of z and t, then I would take the real part of e to the j omega t here, and it would be times this. And I would have times ex 0 plus e to the minus gamma z plus e to the j omega t times ex 0 minus e to the gamma z. And let me just also make sure we know this. The gamma itself was equal to some alpha plus j beta is equal to the square root of j omega mu times sigma plus j omega epsilon. Y'all with me on this class? All right, I come here. You pretty much know I'm going to end up getting a cosine out of this thing, right? You can see that happen. So what I'm going to do is say this. When I replace gamma by alpha plus j beta, I would get this. I would have ex 0 plus, then it would be e to the minus alpha z, then it would be the cosine of omega t minus beta z, and you would have plus ex 0 minus e to the gamma z times cosine of omega t plus beta z. And that would be the time domain solution. And it would be in the AX direction, of course. But it's propagating either in the plus or minus z direction. This part, make sure you write down. Some of you remember this probably from doing transmission lines. But you see when we have omega t minus beta z, that's a wave traveling in the plus z direction. Just put an arrow under there. I try to make sure you understand that. That's plus, that's going in a plus z direction. This would be a wave going in the negative direction. Now, something that always happens is as you propagate, as the wave's moving, it loses amplitude if there's loss. You see that e to the minus alpha z there? As z gets larger and larger and larger, this thing's decaying down to nothing. You all follow me on that? That's a wave going in the plus z direction. For this one, this is e to the alpha z, but it's going in the negative direction, right? Just think about this. As z gets negative, you might say that way, then this will become smaller and smaller and smaller. You all follow me? It's basically, if it's going in the other direction, this thing will start attenuating. And this omega t plus beta z tells you the direction. If it's got a plus there, it's going in the negative direction. If it's got a minus, it's going in the positive, okay? I'm just trying to make sure I cover all my bases with this stuff. So that's the time domain solution for plane waves. And again, I'm sticking with Wentworth's book, X polarization, moving in the z direction. We could write a more general form, but it doesn't really serve the purposes of what I'm trying to show you. Now that's plane wave propagation. And we've got gamma is equal to alpha plus j beta. And really, you see we get that from there, right? Basically. Now, something we need to do, whenever you take a look at equations like this, I try to just focus on some of the really important things. From now on, we're going to forget about this negative traveling wave, all right? We're only going to take a look at positive traveling wave. The reason is because this tends to just get in the way of the actual, of seeing the real, I guess, some of the great truths that are happening. Now that's an equation for propagation. If you took a snapshot in time of this, just freeze time and you put z here, what you would see is something like this. And I hope you can appreciate it. If you freeze time, make it t equals 0, you're going to see this. You all with me? Now, if you let time go by a little further, you would see this. And it would appear that the front of the wave right here had moved, and it's moving in that direction. You all follow me? I'm just trying to give you a picture in your mind of what's going on. Again, I'm freezing time, take one frame, then move it ahead a little, freeze time, and take a look. When I look at this, there's a couple of very important things that happen. You see how really the phase of this point, say at t equals 0 and t equals some additional time, the phase right there is the same. You all follow me on this, class? This is phase velocity we're talking about next. All right, now we did this when we were talking about transmission lines, but the way you get phase velocity, we know this for a constant phase, I could just say some value c was equal to omega t minus, in this case, beta z, right? That's a constant. If we could somehow jump on top of this thing and move along as time went by, we would see we were riding the crest, we were on the phase velocity, if that makes sense, right? The way to get phase velocity is this. Take the derivative of both sides, you get 0 is with respect to t is equal to omega minus beta times dz dt. And then dz dt is the phase velocity of the wave, and that's equal to omega over beta. Okay? That's important. Now that's true for transmission lines as well. Do you remember that? How many remember that for transmission lines? All right, sure. That's phase velocity. Matter of fact, that's a general physics principle. If you have something that's time harmonic, that's varying as either a sine or cosine, That's how you get the phase velocity. So, if you look at this, the phase velocity, there's a couple of important parts to this. First is, what happens when you're in free space? So I'm going to try to do this. So that's phase velocity. So now we have gamma is equal to alpha plus j beta is equal to the square root of j omega mu times sigma plus j omega epsilon, right? So now we're going to take a look at the phase velocity for a couple of different cases, all right? First one is this. If we are in free space, so free space means sigma is equal to 0, epsilon is some epsilon naught, mu is some mu naught, right? With me? That's a vacuum, think of it that way. Free space is a vacuum. If I look at the phase velocity, right? First, I need gamma. Gamma would be 0 plus, and it would be just j omega times square root of mu naught epsilon naught. And therefore, that means beta is simply equal to omega times square root of mu naught epsilon naught. I'm going to stop for a second and let you see it, figure it out for yourself. Just take a look at this equation up there and plug in those values. If sigma is 0, I have square root of j omega mu times j omega epsilon. Square root of j omega squared is j omega, right? That's that. And then square root of mu naught epsilon naught. Y'all follow me on this, class? Everybody? All right. Now, phase velocity is what? It's omega divided by beta, or omega divided by omega square root of mu naught epsilon naught. And this is a very famous fact. What is the 1 over the square root of mu naught epsilon naught from physics? It's the speed of light in a vacuum, right? In a vacuum. And normally we label that C. Well, it's about 3 times 10 to the 8th meters per second, slightly less than 2.99 something else. It's a bunch of, it's one of those things, the way they determine that is with some precision instruments. And I think Michelson-Morley was one of the first people to both measure the velocity and also determine the speed of light was independent of the reference frame. But that's long ago. Anyway, that's in a vacuum what you get. Now, if you have anything that's lossless, I'm going to erase that. So, 2 in a lossless region. A lossless region just means sigma is 0. Then you can see when I have that equation, gamma is going to be equal to, since sigma is 0, I have j omega mu times j omega epsilon. It's still going to be j omega, but now we're going to have the square root of mu naught epsilon naught times square root of mu r epsilon r. And that's really 0 plus j beta, so beta is this. Beta is simply omega times square root of mu naught epsilon naught times square root of mu relative epsilon relative. And then you can see that the phase velocity in a lossless region is simply omega over beta, or if I take a look at this, it's going to be 1 over square root of mu naught epsilon naught square root of mu relative epsilon relative, and that means it's going to be the speed of light divided by square root of mu relative epsilon relative. This is also important to notice. you'll notice how anytime we have materials that are made of, say, epsilon relative greater than 1, or mu relative greater than 1, that the speed of light slows down. Now I have something to tell you about that, because that's not quite true. This is the speed of light for the bulk of the wave movement. Actually, what is happening is the individual photons are ricocheting. All right? They're ricocheting around. You all know that light's made up of these, they call them corpuscles sometimes, these individual photons. You've all heard that term, haven't you? I don't know if you've had modern physics or how, you haven't had, well, if you haven't had modern physics, you probably can't appreciate this fully, but light is a wave, yes, but it is made up of photons, which is a little ironic, because that means it has both particle and wave properties at the same time, which makes it very hard to discuss in classic physics sense. But nevertheless, if we talk about the entirety of the wave that we see macroscopically, it would appear that the velocity of light is slowing down when we have different values of epsilon relative to mu. That's the propagation velocity of the bulk of the things, and it's called the ensemble of photons. But actually what's really happening is these little photons are ricocheting slightly, and that ricochet slows down the net propagation direction. So remember that. The velocity of light, photons always move at the speed of light, but they bounce. They bounce off things. So that's something a little different. The physicists would do it probably with scattering theory, and it'd throw you a lot more information. I don't think you can really would appreciate the reason for it. But this is the truth. So that's the velocity when you have any kind of a lossless material that's not free space. Now we go one step further, and we get the velocity when we have lossing materials. They call them good conductors. So 3, now we're going to get the velocity, but here we're going to get it for a good conductor. Got to ask you, how would you define a good conductor? If you were asked, your boss asked you this. It's a legitimate question. Anybody? Go ahead.
One that gets the train in the station at a good time.
Yeah, then you would be fired. But anyway. If you talk about a good conductor, what does it mean to you? Is copper a good conductor?
Yeah.
Yeah. What about silver? Gold? Yeah. They're all aluminum, metals, right? Why? Because mainly they have very little resistance for anything that any kind of current you're going to apply. You don't even worry about the resistive drop on wires usually, right? But what it's really saying at the microscopic level, a good conductor has a value of sigma that is much, much greater than omega epsilon. Now remember, omega epsilon is a term that's weighting the E field, and it's related to the displacement current. Do you all remember that? Remember, we have partial of D with respect to T, that's displacement current. Well, partial of D is with respect to T is J omega, and D is epsilon E. So J omega epsilon is displacement current, J omega epsilon E. And if you look at conduction current, it's sigma E. So if I took J conduction, it's equal to sigma E. J displacement is equal to J omega epsilon E. So whenever the magnitude of J conduction is much, much greater than the magnitude of J displacement, in fact, you have a good conductor. This is for a given E field, and that's what it means right there. Microscopically, that's what it means. Now, if you have a good conductor, things happen that aren't apparent. First of all, I come over here and I look at gamma. Gamma is equal to the square root of J omega mu times sigma plus J omega epsilon, right? Now, I said it was a good conductor. That means the magnitude of sigma is much, much greater than omega epsilon. Can you all follow me on this one? Much, much greater. 5, 6 orders of magnitude. So that means I can get rid of that. Y'all see how I have just sigma there. I don't have sigma plus J omega epsilon. Follow me, guys? All right, now what happens there? Well, this is actually, when I take a look at J, if you wanted to write J a couple different ways, J is actually equal to what? you could say it's equal to e to the j pi over 2. Isn't that right? Just think about that. J is really what? Well, it's the square root of -1 is one take on it. It's really 1 at an angle of 90 degrees, right? So in the phase domain. This is 1 at an angle of 90 degrees, right? What's the square root of j? Isn't that e to the j pi over 4? You with me? If you take the square root, it's really to a half power. If I take this to a half power, I get j pi over 4, don't I? All right, what is that? Well, that's the cosine of pi over 4 plus j sine of pi over 4, isn't it, guys? What's the cosine of pi over 4? Cosine at 45 degrees, anyway. 1 over square root of 2, isn't it? What's the sine of 45 degrees? Same thing, right? So this is really equal to 1 plus j divided by the square root of 2. Now I put that there for a reason so you can see what's going to happen. Y'all with me, everyone? Follow me? There's square root of j, isn't it? Y'all see it right there? So now I can say this is really 1 plus j divided by the square root of 2 times this mess, which is equal to square root of omega mu sigma. Now, I'm not quite done yet, but I think some of you are at least picking up on what I'm about to do. Now, that's square root of 2, right? Came from over there. I can stick that under this radical cap. Sure, I can get rid of that and just make this, put 2 under there. Y'all with me? Take a good look. Now, what's omega in terms of f? Anyone? 2 pi f, right? If I replace omega with 2 pi f divided by 2, I get pi f, don't I? I'm going to do that. And here's the kicker that you write down. Make sure you write this down. You can say gamma is equal to alpha plus j beta, and alpha in magnitude is equal to beta is equal to the square root of pi f mu sigma. Y'all with me? This is for a good conductor. Now the reason I did it that way, I mean, y'all see this right here? I'm doing it to show you the trick. Once you get down to that point, I have beta, right? Now, take a look at the velocity for a good conductor. Velocity is still the same. Phase velocity in a good conductor is omega divided by beta. And I can have it with this and that, doesn't matter. So omega is 2 pi f over that, which is square root of pi f mu sigma. That's phase velocity in a good conductor, right? Keep watching, almost done. Now, you see, and I'm gonna tell you what, I'm gonna erase this so you can see this better. So now I can say phase velocity, well, I got square root of pi, or I mean, we got pi divided by square root of pi is really square root of pi on top, right? So I got 2 times square root of pi. Then I have f divided by square root of f. That's going to be square root of f on top, so it would be square root of pi times f. Then it's divided by square root of mu sigma. Now I have a comment here, and this is the reason I did this. Remember, that's phase velocity for a good conductor. Take a look at that as f goes to 0. What value is it going to? 0. So that means for a good conductor, as we approach 0 frequency, the phase velocity is 0, right? It was the speed of light just a little bit ago in vacuum. Now, the phase velocity of these waves basically goes to zero. Here's the thing about that, and that people get messed up on. You know, if you have a wire, conducting wire, and you drive a differential input, you get current flow, right? The actual velocity of the wave, if it's a propagating wave, on that wire is going to be about the speed of light. It's really due to the dielectric between the insulating wires. However, if you had a big fat wire, the rate that the actual electric field propagated towards the center of the wire, it's propagating downwards in the direction of the center of the wire, would get slower and slower and slower and approach zero. And this is one of those weird things. I'll have to show you some more about this because I think I am out of time. Anyway, I wanted to cover those things. We're going to do characteristic impedance and a few other things on Wednesday. I'm going to give you some homework that will set you up for this, so you won't be taken off guard, because some of this stuff is very abstract if you don't see it worked out. Did you all have some of this before or not in physics?